All right, so today we're going to look at circular motion. Quick review. Acceleration is a change in velocity, and velocity is a vector, which means an object will accelerate if it slows down, or if it speeds up, or because of its velocity is a vector, if it changes direction. So any one of those three will cause an acceleration. So from Newton, we know that anytime an object accelerates, there must be an unbalanced force acting on it. So if an object is changing directions, and therefore accelerating, there must be a force acting on it. Newton's first law says objects remain in motion in a straight line unless there's an outside force acting on them. So we know that if an object is changing direction, it's not moving in a straight line, there must be a force acting on it. Now, there's very complicated ways that forces can act on objects, but we're going to consider a very simple one. Imagine an object is moving right here, the blue object, to the right, and we act with a force on it in this direction, perpendicular to its velocity. If we do that, we will change its direction. Instead of moving this way, it will now start to move this way. If we continue to apply that force perpendicular, it will continue to change direction and it will move in a circle. So circular motion occurs when a force acts perpendicular to the velocity. If a force acts perpendicular to the velocity, that changes the direction of the velocity, but it doesn't change its magnitude. It doesn't slow it down or speed it up. It just changes the way it's going. So if you are standing and spinning a rock in a circle, the rock is right here. It is moving in this direction. This is the direction it will continue moving unless a force acts on it. If you pull on it with a string perpendicular, so its velocity is going this way, the force is perpendicular, it will change its direction, and you will keep applying that force perpendicular, and that will cause it to change directions. So a force that continuously acts perpendicular to the motion of an object causes the object to move in a circle. And because the direction of the force is pointing towards the center of the circle, we call this center-seeking forces or centripetal forces. They always act towards the center of the circle. So the centripetal force is not a new force. It's not like you have normal forces and friction forces and now centripetal forces. It is really just the job that a regular old force is doing. So the forces we've encountered, friction, gravity, tension, applied forces, spring forces, if any of those forces act perpendicular to the velocity of an object, we say they are acting as a centripetal force, okay? So a centripetal force is not the type of force. When you label an arrow, you can't call it FC. That's not a type of force. It's either a normal force or a tension or an applied force. It's just the job that it is doing. So for a car that's moving in a circle, it's the friction that causes the car to move in a circle. So the friction exerts a force perpendicular to the direction it's moving because you turn your wheel slightly. You can imagine that if the road was icy and you had no friction, this car would just continue to go straight. It would follow the path that its inertia is taking it. So the force that the friction exerts is perpendicular to the direction the car is moving. So in lab, you did a rudimentary lab where you try to investigate how the velocity depends on the force, and the straightest line you could get was when you took the square root of the force. And so what you found roughly was that the velocity is proportional to the square root of the force, or to think about it differently, the force is proportional to the velocity squared. So, how much force do we need to make an object move in a circle? Well, to make an object move in a circle, it depends on the mass of the object. Heavier objects have more inertia, and so you need a bigger force to make them change directions. It depends on the radius of the circle. A bigger radius means you're not changing its direction very much each time, and so you don't need quite as much force. So we would expect that the centripetal force is inversely proportional to the radius, and it's proportional to the velocity because the faster it's moving, then the more the direction it's got to change in order to move in a circle, and that would require more force. So we're going to just do a simple little derivation here. If your eyes gloss over and you don't get all of this, it's okay. But if you think about an object moving in a circle, at one point right here it has a velocity vector v, which is pointing in this direction. A little while later, the velocity vector is pointing in this direction. The velocity vector has changed a little bit, not much. If I draw those two velocity vectors over here on the side, it's going to look like this. The first one right here is pointing in this direction. The second one, this one here, is pointing slightly to the right of it. And the difference in those two velocity vectors is the change in velocity. So the change in velocity is actually in this direction. Now, we can use a little bit of trig. The definition of an angle in radians is the arc length. So that's this distance right here, the arc length, divided by the radius of the circle, which is r, because this is moving in a circle with a radius r. So the definition, the angle here, is equal to the arc length divided by r. But these are similar triangles. This is the exact same angle that these two guys are separated by. And so we can also apply it to this equation. The arc length, delta v, divided by the radius, v, is equal to theta. So that looks like this. So we can take these two equations, which are equal to each other, and we can set them like this. So s over r, the arc length divided by the radius, is equal to the change in velocity here divided by the velocity. So that's where we get that from. Now, this arc length, how far it goes here, is equal to the velocity times the time. So if we know how long it takes to get from here to here, and we can take the velocity times the time, that tells us the arc length. So that gives us this equation here. The arc length is equal to the velocity times the time that elapses between the position here and the position there. So we can take this value for the arc length and substitute it into that expression. So we will have v times delta t, that's this, divided by the radius r. So we're basically just rewriting this equation, but we're substituting this in for s. We'll get this equation here. If we cross multiply, we'll get v squared times delta t equals delta v over r, which we can then rearrange, and it looks like this. The change in velocity divided by delta t is equal to v squared over r. And the change in velocity divided by the time it takes to change the velocity is the definition of acceleration. And so we get that the acceleration of this object as it's moving in a circle is equal to v squared over r. Okay, so that's a simple little derivation that kind of shows you where the whole centripetal force comes from, v squared over r. All right, so if something's moving in a circle, it must be accelerating. The direction of the acceleration must point towards the center of the circle, and the acceleration must have the magnitude given by v squared over r. That's the acceleration of an object moving in a circle. So if we think about accelerations, these three things are true. Okay? If we think about forces, if an object is accelerating, there must be an unbalanced force on it. So if an object is moving in a circle and it's accelerating, then there must be an unbalanced force acting on it. The direction of the acceleration is pointing towards the center of the circle, so the direction of the unbalanced force must be pointing towards the center of a circle. And if the acceleration is v squared over r, then the force has got to equal m times the acceleration, which is m times v squared over r. And so this is how we find the force that is required to make an object move in a circle. Things do not move in circles on their own. They require an external force, and this is how big the force has got to be. If the force is not exactly this big, it will not move in a circle. So that's where this equation comes from. The centripetal force, the force required to make an object move in a circle, is m times the centripetal acceleration, which is v squared over r. On your AP reference sheet, it'll tell you a sub c equals v squared over r. To find the force, you have to multiply it by the mass, so it's mv squared over r. That's the big idea. So, a couple calculations. How much tension do you need to apply to keep a 0.5 kilogram rock moving in a horizontal circle? The radius is 1.2 meters, and it's moving at 5 meters per second. So, we can just draw a simple little diagram. We know the mass, the velocity, and the radius. And so we can just simply find the centripetal force that is required. It's mv squared over r, and it looks like that. I did not apply Newton's laws, so I don't need a free body diagram for this problem. I'm just calculating the force required to make it move in a circle. Okay, second one. I've got a brick, and it's on the edge of a merry-go-round, and the merry-go-round's going 6 times around every minute. So we got to first find the velocity. Once we know the velocity, we can find the force that's needed to make it move in a circle. So to find the velocity, what we have to realize is if the radius is 1.5 meters, we can find the circumference. And it goes around 6 times in 1 minute. So that's really just a conversion. If we take the velocity is the distance over the time. The distance is 6 circumferences divided by the time. 6 circumferences is 2 pi r times 6 divided by 60 seconds, and that turns out to be 0.94 meters per second. So now we know the velocity, we can figure out what force is required to make it move in a circle. So the force to make it move in a circle is mv squared over r. We know the velocity now, we can plug that in. It takes 1.18 newtons to make this brick move in a circle. Okay? All right, now, bit of a misconception. There is no centrifugal force. If you are on a merry-go-round, there is no force pushing you off the merry-go-round. The tendency for you to fall off the merry-go-round is due to your inertia. Your mass wants to continue moving in a straight line. The merry-go-round is trying to leave out from underneath of you, and you need a force inward to make you stay on the merry-go-round. Without that force, you would continue in a straight line and therefore fall off the merry-go-round. So there's no centrifugal force, it's a centripetal force. The centrifugal force is really just what feels like a force pushing you outwards, but it's really an inertial effect. It's the same idea as if you are in an airplane and the airplane is accelerating down the runway. It feels like something is pushing you back in your seat, but there's nothing pushing you back in your seat. It's your inertia trying to remain where it was, and the airplane seat pushing forward on you, causing you to accelerate forward. All right, so a third example. I've got a brick on a merry-go-round, and the merry-go-round is spinning. The question is, what keeps the brick on the merry-go-round? Well, I think it makes kind of sense that friction is what keeps the brick on the merry-go-round. If the merry-go-round was really, really slippery, as it spun faster and faster, the brick would slide off. So friction makes it move in a circle. So here's a side view of the merry-go-round. Here's the axle of the merry-go-round, here's the merry-go-round, and here's a brick on the edge of the merry-go-round. And so right now the brick is moving away from us. If I were to draw the forces acting on that brick, it would look like this. Here's the brick. Gravity's pulling down on it. The surface of the merry-go-round is pushing up on it with a normal force. And because it's moving in a circle, there must be an unbalanced force. The brick is trying to slide off to the right, and so friction must be acting to the left. So friction is a force to the left. There is no force pushing it off to the right. That's its inertia. So this is the free body diagram. If we apply the equation to find the friction force, it's mu times the normal force. And in this case, because the normal force and the gravity force cancel each other, they're equal in magnitude, I can put in for the normal force mg. So this is the friction force. And now I apply Newton's law. Because the center of the circle is to the left, I call that the positive x direction. So the force is to the right, which is the friction force, minus the forces to the left, which is none. That's the net force. That's got to equal the mass times the acceleration, which is v squared over r. So another way to say this is, when something's moving in a circle, the unbalanced force, this, must equal mv squared over r. So the unbalanced force is really just the friction force, and that's got to equal mv squared over r. So if we put in the friction force, which is mu mg down here, we get mu mg is equal to mv squared over r. The masses cancel, so it turns out it does not matter what the mass of the brick is. You can find the velocity, the maximum velocity, by mu sub s times g times r. And then if you plug in those numbers, that's 2.27 meters per second. Okay, so in this case, I applied Newton's law to find the unbalanced force to solve the problem. And so I had a free body diagram. All right, one more nuance to look at. Sometimes we call the apparent weight the normal force. So another way to refer to the normal force is the apparent weight. So imagine you're on an elevator and the elevator is accelerating upwards. The force acting up on you has got to be greater than gravity pulling down on you in order to make you accelerate upwards. So that force pushing up on you, that normal force, it's the weight you feel like you have. So we call it the apparent weight, but apparent weight is just normal force. So imagine I've got a 100 kilogram student and they're on a roller coaster. So here's this roller coaster with the student. It's 100 kilograms. They are on a level track. They are moving from left to right, but the important thing is that the track is level. And so they are not accelerating upwards or downwards. If I draw the forces acting on them, the normal force pushes up, gravity pulls down, and since they are not accelerating in the y direction, those forces must add up to 0, which tells us that the normal force must equal mg. So for a 100 kilogram student times 9.81, that's about 981 newtons of force pushing up on the student. That's the weight they feel. But what happens when their same student is at the bottom of a roller coaster loop? So now they are moving in a circle. Even though they're right here at the bottom, they're moving in a circle, which means there must be an unbalanced force on them. Gravity pulls down with the force of Fg. But now the normal force, the track, must push up on them with a much greater force because it is the unbalanced force that makes them move in a circle. If these two forces were balanced, they would not be moving in a circle. So this normal force must be bigger than their weight now. And so at the bottom of a roller coaster, you feel heavier. Your apparent weight increases. To figure out what the apparent weight is, we are going to apply Newton's law. The force in the positive y direction, Fn, minus the force in the negative, Fg, must equal m times a. But what is a when you're moving in a circle? It's v squared over r. So the normal force minus Fg, that's the unbalanced force, must equal mv squared over r. We can then solve for the normal force by adding F sub g to both sides. Since F sub g equals mg, it actually looks like this. And then using the numbers in the problem, you can plug in the numbers and you can find out it's about 5,100 newtons. So remember, when they are on a level track, the normal force was about 1,000 newtons. Now it's about 5,000 newtons. We would say that their apparent weight is about 5 times their usual weight, or we would say they are experiencing a g-force of 5. So this normal force is about 5 times the regular force that they experience when they're not moving in a circle. So it requires a lot of force to make them move in a circle, and that's the bottom of the loop. So the normal force must be big enough to cancel gravity, and it must be even bigger to make an unbalanced force towards the middle of the circle. Now think about what happens if you are at the top of the loop. Now gravity pulls downwards, and the track pushes perpendicular on you. It also pushes downwards. So these two forces together form the unbalanced force that makes you move in a circle. I'm going to call this the y direction. And so when I apply Newton's law, there are no forces in the positive y direction, so I'm going to get minus Fg minus Fn, and that equals minus mv squared over r. It's negative because it's downwards, so these are all downwards. So you could have just as well said that the force of gravity, if this is the positive direction, plus the normal force must equal mv squared over r, and this is the positive direction. We can now solve for the normal force. It looks like this. We subtract the weight of gravity. And if you plug in the numbers, you actually get only 50 newtons. So at the top of the roller coaster loop, the track does not have to push on you very hard to keep you moving in a circle, because most of the force that's making you move in a circle is your own weight. Gravity is acting downwards, keeping you moving in a circle at the top of the loop. The track doesn't have to push very hard. And if you were going a little bit slower, the track wouldn't have to push at all. You would be momentarily weightless at the top of the loop. So you'll do some problems where you will apply these principles to a car on a roller coaster loop. Okay, all right, so there's a problem set for you to work on. Good luck getting that done. Help each other, and If you're completely stuck, I can help you with those when I get back. This is not due until after fall break. It is not on the first quarter grades, but don't waste time today because we have a lot to do. Okay? All right.